Hi, I'm James Wagner from the Survey Research Center at the University of Michigan, and I'm going to talk today about comparing methods for predicting costs in a responsive design framework. And I think survey costs are probably an understudied problem, so we're excited to contribute to that discussion. I'd like to acknowledge my co-authors, Mike Elliott, Brady West, and Stephanie Coffey. We've been working together on a project that I acknowledge here on this slide. It's a NIH-funded research project. And also a disclaimer from the National Survey of Family Growth, the sponsors of the study, NCHS. So as an overview, today I'm going to talk about some background on responsive survey design, and then I'm going to talk about a problem, the specific problem we're going to be discussing today, which is the need for predicted costs under alternative designs. Then I'm going to spend a little time explaining the data. I think the data are somewhat complicated, so you'll have to bear with me as I discuss those data. And then the methods we're going to use, which is a comparison of multi-level regression models with something called Bayesian additive regression trees. And then I'll finally present the results and have some conclusions for you. So responsive survey design is a response in part to uncertainty, which has become an issue in survey design. So for example, if you want to try and predict response rates under competing designs, it's often difficult to do so. And RSD makes use of incoming data from the field to address that uncertainty. So as we have more data under the current protocol, we can make better predictions of what's going to happen. And Groves and Haringa detail this responsive design in a paper in 2006, which is listed in the references section of the slides. Now, the idea is that you develop indicators of cost and error. Okay, and I think the focus has probably been more on the error side. But if you look back at the Groves and Haringa paper, you'll see that they do a fair amount of discussion of costs. And then use planned intervention when either costs increase or errors either stabilize or increase. Okay, so there's some kind of decision rules in the background, but here it's important to note that costs are an important part of that decision rule. And costs and errors vary over time. So it might be hard to predict them. Traditionally, responsive survey design has used proxy indicators for both of those. So costs are often measured through a proxy indicator such as call attempts, the number of call attempts it requires to complete a case. And non-response error is judged, for example, by looking at the stabilization of estimates. All right. If a phase has stopped changing an estimate, then it's said to have reached its phase capacity. And maybe another phase would bring in a different kind of respondent and might help address non-response error. So there's been some research on this topic, and including research on the NSFG, specific to the NSFG. And the problem is that inaccurate indicators, if you're using a proxy indicator, might lead to an inefficient design. And so the particular problem we're interested in addressing today is, can we improve the accuracy of cost predictions? Now I'll talk a little bit about the survey that we're using as sort of an input to our simulation study, and that's the National Survey of Family Growth, which we conducted from 2011 to 2019 on behalf of the National Center for Health Statistics. It's a continuous data collection. That is, there's a new sample released every quarter, and it's a two-stage data collection. That is, we screen households to identify eligible persons. Once we've found an eligible person, we conduct the main interview with that selected person, and that's the topical survey of the NSFG, which is about family formation, reproductive health, and other topics. There's two phases of data collection using the phase terminology from responsive survey design. And phase one is generally a 10-week data collection, and a subsample of remaining cases at the end of phase one are then given a phase two protocol, which includes oversampling higher likelihood of interview cases and highly likely to be eligible cases, reducing the interviewer workload, and changing the data collection model where we increase the interview token of appreciation and we change the interview behavior with having them focus more effort on fewer cases. Now, after phase two is complete, we combine the data from the two phases using weights. Now, in our particular situation, we want to use the data available at the time the predictions need to be made, okay? So that's going to make this a little more complicated. Now, paradata are often highly correlated with interviewer hours. So if I had the paradata from week 10, I could predict how many hours would be used in week 10 pretty easily. Our problem's a little different. We want to predict future time periods. And we're going to have paradata that are available earlier to predict the future. And so we're going to have to use lagged values. Okay, and so here I'm showing a simple chart where each of these little blue squares represents a week in that 12-week quarterly production cycle, remember? And we want to use the data from week 4 to predict what will happen in the future in week 6. And the reason we use that two-week lag is because we want to predict at the end of week 10 the outcomes of week 11 and week 12. Okay, so we're essentially predicting 2 weeks into the future, and we're going to use lagged values for those predictions. Now, the data include a number of different types of data: the interviewer ID, which is important, the phase, all right, so that's the key design change, and then the lagged value of the following kinds of things: area characteristics, so you could think of neighborhood, census division, basically data coming from the sampling frame um, that, that give characteristics of the area. Interviewer observations about the neighborhood, the housing unit, and the sampled person in the case of, of, of this survey, and then also commercial data that are merged onto the sample frame. Now, these data aren't available for every case, but where they are, they include things like the age of the first person enlisted in the household and so forth. And importantly, paradata, so the number of screened interviews, the number of trips made in a week, and the number of active lines, for example. There are a number of variables. Now, these variables are summarized to the interviewer week level. So each interviewer works a week, we create a record for that week, and we summarize information to that interviewer week. So call attempts have sample characteristics, right? So we got to keep this straight in our head. Call attempts each have a sample characteristics. Now, if you call a case multiple times, you're just repeating those same sample characteristics. Those are fixed. But the number of call attempts will change. Now, how do we summarize those to an interviewer week level? Well, for all of the sample characteristics, we take the mode of the attempts made by the interviewer. So, for instance, we take the modal urbanicity from the attempts that an interviewer made in a week. For a continuous variable, we take the mean. So for example, the mean population eligibility rate from the attempts that were made. Again, these characteristics are lagged. And for some variables, particularly the paradata variables, we use the sums. All right, so the number of completed screening interviews 2 weeks prior to the week being predicted. Again, we're lagging those values. All right, so hopefully those examples help you understand the structure of the data that we're using for this prediction problem. Now, we use data from the previous quarters, so we're going to use data essentially from quarter 1 through quarter 27, but we're always using the data that would have existed before we wanted the predictions for phase 2 in a quarter. Okay, so we use data from the previous quarters and the current quarter phase 1 to predict the phase 2 costs of the current quarter, where the current quarter could be 22, 23, 24, 25, 26, or 27. All right, so we're not using the hours we want to predict as an input to the prediction model. Okay, just to be clear about that. And the outcome variable is phase 2 interviewer hours. And this is the major cost driver of the phase. There are other costs, the incentives, the mailings, but those are not predicted in these models. We would predict the incentives as a function of the number of completes that we predict would occur. And we know the sample size ahead of time, so we can pretty accurately predict the mailing costs. We're focused on the interviewer hours, which is actually the bulk of the costs in this design. And we're going to use 3 methods of prediction. The first is a multi-level regression model with a random intercept for each interviewer. And all the covariates that are described earlier are included in the model. And I have those in the appendices of the slides. We're preparing a paper that will have those as appendices. So the variables will be available to look at. Then we have the second class of models, which are Bayesian additive regression trees. Okay, and they're additive, which is important. So it's really a sum of trees method. And here I'd encourage you to look at the Chipman paper, which I think is a really excellent paper, and they go through in detail the approach. We're not going to discuss an important element of these models, which is how do you choose the priors, right? I don't have time today, but it's in the paper, the information. We had a lot of help from reviewers on making choices on priors that constrain the inclusion of predictors. And it's possible then to examine how frequently each predictor is included. In the multi-level models, you get a bunch of coefficient estimates. You don't get that from a BART model. You get the predictions. They're trees. But it's possible to see how often a variable is entered into those BART models to branch one of those trees. The treatment of interviewers in the Bayesian additive regression trees can be handled in two ways, and we try both. One is as a random intercept, essentially, and the other is a fixed effect, where we have an indicator for each interviewer, and that indicator is allowed to create splits in the tree models, the same as any other indicator variable. Now, we're going to compare using two approaches. First, we're going to look at the total predicted versus observed hours in phase 2. How accurate is the prediction of the total? Now, interviewers get different pay rates across different settings in the country. So we're going to use interviewer level predicted versus observed hours in phase 2 as another comparison. And we're going to use two measures of accuracy. One is the mean squared error, and the other is the mean absolute error here. And you see both of those defined. Again, we have predicted values, but the observed values that we're comparing them to were not used in estimating the models, either the Bayesian model, the BART models, or the multi-level models. Now, the results. The first thing we want to say is that interviewers are consistent, and this can be measured in several different ways. One is in the multi-level models, the inter-cluster correlation is quite high when we use that random intercept model. Here's the range across the 6 quarters that we looked at. Now, if we look at the fixed effect BART models, we can look at the 20 most frequently included variables, as I described a moment ago, and 8 of those are interviewer IDs. Now, these aren't their ID numbers, they're just a random ID that we've assigned to them, but you'll see that 8 of the 20 variables are interviewer IDs. Another indication that interviewers are consistent is the most important variable. I should say the variable that enters the BART models most frequently to create splits is the number of hours worked 2 weeks prior. Okay, so it's an indication of consistent behavior across time. Now, in terms of the accuracy, we have the total comparisons of the total hours that are observed to the predicted total from each of the 3 models across the 6 quarters of interest here. The red line is the observed hours, and so we want to be as close to that red line as possible. Now, all 3 models include the observed value in the confidence intervals generated here for quarters 22, 25, 26, and 27, but none do for 23 and 24. However, the random intercept BART model comes closest for quarter 23 and 24 compared to the other 2 models. Now, the other comparison that we wanted to make is here, and that's the interviewer week level. So here we're saying each prediction for each interviewer week. There's about 30 interviewers. There's 2 weeks in phase 2. So we've got about 60 predictions, and this is the one for quarter 27. We're showing the predictions for quarter 27. Similar results for all the other quarters. And the random intercept BART model produces the closest observed and predicted values. Observed values on the x-axis, predicted values on the y-axis, and the red line would be perfect agreement between observed and predicted. And it looks like that random intercept BART model comes closest. We can look in detail at those 2 comparison statistics we described, the mean absolute error and the mean squared error. We defined those earlier. And what you'll see, the mean absolute error on the upper row, the mean squared error on the lower row, and each bar represents the error from the predictions for that model type. And across all of the models, the random intercept BART model got the best results, the most accurate predictions by each of these measures. I will note that in quarter 23 and quarter 24, especially, the random intercept BART model did better than in the other models. So the conclusion, the existing methods can be used to predict survey costs, right? And we can look at machine learning techniques. We've only looked at one, there are many others, and we think this is an exciting area of research. We would like to see other papers where people try other methods to predict survey costs. In this problem, knowing the interviewer is very useful since their behavior is consistent. That's true across all the different types of models. For this model, the BART models improve the predictive accuracy compared to the multi-level model, including the interviewers as a random intercept in the BART model produced the most accurate predictions. And that's so that would be our preferred model. So that's it. I've skipped a lot of information I think is useful. In particular, how do you select the prior information for the BART models? And you can see more of that information in a forthcoming Journal of Official Statistics paper. We just sent back the proofs, and so we think that should be coming out soon. If you're interested in this and want to learn more or want to give me some feedback, you have my email address here. And in the slides, I'll note we have references and we have detailed descriptions of the variables that were included in the model. So thank you very much.